This is the Amp Hour Podcast, released December 4th, 2022. Episode 611. Grad School Time Capsule with Joshua and Zach. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
I'm Joshua Vasquez of the Allen Institute and the Jubilee Project.
And I'm Zach Ferdine of Commonwealth Fusion Systems.
Hey guys, welcome back. So here's an interesting story. I recorded with Joshua and Zach in 2018, I think it was. Do you remember what year it was, guys? It was definitely pre-pandemic.
I think it was 2019. It was right after Teardown.
2019.
I think it was 2019.
Okay, yeah. So yeah, it was at Teardown.
Yeah.
Yeah, I guess I should look that up too, because we had a bunch of shows from Teardown, and I recorded a bunch, and I had thought I lost the audio, and so the three of us were at a party and we were recording. So it's going to be somewhat good audio, but we're going to put it at the end of the show. And the interesting thing is that Joshua and Zach were just about to go into grad school, and I saw them both at SuperCon, which is the conference we were all just at in November. And they are no longer in grad school. And so I thought, because I've been holding onto this audio for 3+ years now, what happens if we listen to them now and then we also get to hear them then? But the really interesting thing is they haven't heard it either. So I don't know. I feel like this is a great audio experience. How are you guys feeling about this?
I trust you, man. I support it.
That's your first mistake. Okay.
I'm curious, so we'll see. Who was this person?
Exactly. So young. Real quick, before we start into the now, let's give a quick little sample of what was 2019 for both of you. So, Joshua, why don't you go first?
Oh, sure. Yeah. Let me think. So I had been in grad school. Actually, yeah. So if it's 2019, I had been in grad school for about a year. And I'd been working on a project. I was really into multi-headed CNC machines. And I was looking into building one. And I was very close to getting one working. At the time, I had just named it Jubilee. And I remember kind of pouring my heart into it. And I was very excited about what I was going to share. We were going to make it open source. Yeah, so I had actually been there. For a year now that I think about it. It's kind of weird because it all
forgotten about
smears into one. Yeah.
Yeah, right. Yeah. Okay. That's great. And you were at UW, is that right?
That's right. I was at UW in Seattle in the HCDE department, Human-Centered Design and Engineering. It's a big mouthful.
Yep. Okay, that's cool. And we're surely going to come back to Jubilee because you even said in the intro that that's part of your the thing that you're still about, which is great. So why don't we switch to Zach? Zach, where were you in 2019?
Yeah, so 2019, I was kind of winding down the startup that I think I was on the Amp Hour to talk about a number of years earlier. So I had started this company called NeuroTinker. We had gotten some funding. We made electronic neuron simulators. It was a lot of fun. It was interesting. We sold a bunch, and then the cost structure was not ideal for the educational market, etc. So I wanted to go back to grad school. So I actually applied. I applied in the fall of 2018 and was accepted in the spring of 2019. And my wife and I lived in Minneapolis. So spring of 2019, we're like, okay, we need to sell our house and we need to move to the East Coast. And selling our house was a total gut job, project thing. So we were like, we need to finish this project. And in the midst of all that, we're like, there's a conference called Teardown in Portland. So we flew out to Portland together. And on the way back, we actually took the Empire Builder train through Glacier National Park. And
awesome.
It was great. Yeah. And then we came back and I got a paint sprayer and, we did stucco work and we did 2 bathrooms and we did all the things that we hadn't done over the previous years and had a big party and then moved on. So, I think when you talked to me, I was really excited
you were like,
oh my God,
hyped.
I'm going to grad school. What is this? This is crazy.
Right. And you were going to MIT at the Center for Bits and Atoms,
right? The Center for Bits and Atoms. Yeah. At MIT.
Yeah. Awesome. Well, okay. So that's the before. And now we had a gap of 3+ years. And then what? So Zach, why don't you keep going? So you're already there. Why don't you keep going?
Yeah,
So
yeah, right, sure. I was at the CBA for around 2.5 years. Yeah, I worked on a number of different projects there. One was on, I kind of was started working on a project on reconfigurable computational systems. The idea being you could build physical computational structures and distribute processing across like a physical architecture, and then those nodes talk asynchronously, and you like basically build a structure to fit the type of problem you're trying to solve. So it was looking at simulation, particle simulation and physical simulations where like close interactions matter, but global interactions for what we were doing didn't.
Is this like smart goo? Is that kind of the idea? Like
Yeah, this is more
sci-fi?
like more crystalline than that. So and more deliberately assembled. So a prior student had worked on paintable displays, like conceptualizing paintable
Oh
displays,
yeah.
where yeah, which is just hilarious. Like the idea is you have a can of display when you like paint it on a
Yeah.
wall and it
Yeah.
becomes a display, which is
It's very
yeah
like Looney
yeah
Tunes,
it
right?
was
Like
yeah exactly. But so he that's certainly in the history of our lab. And I did some other projects, one on magic angle spinning NMR, which is a technique for understanding atomic scale resolution molecular structures of crystalline solids. So that was like a laser machining project. And I did a lot of work with Fab Labs. So we remotely deployed Fab Labs to in Nepal and Bhutan while I was there. I didn't unfortunately get to go because there was a pandemic, but we sent a wire
right.
EDM to Bhutan, which was kind of neat.
Yeah, and that's kind of a common thread between you and Joshua as well, right? So Joshua, you were in a similar. So your PI was also a former guest of the show, right? Nadia Peak.
Yeah,
Yeah,
yeah.
and she was from that same lab that Zach was in.
From the CBA, yeah, and
Yeah,
she had
right.
just started a lab over at UW called the Machine Agency, or just Machine Agency, my bad.
Mm-hmm.
And I was like in her crop of first students.
Oh, cool. Okay, that's great. Yeah. So why don't we switch to Josh again? So we're going to kind of ping pong back and forth
Sure.
here, but why don't we switch to Josh real quick, just to get a feel for like the things that you did. We're going to get into the ultimate outputs, but yeah, Josh, and feel free to ask each other questions too. I feel like this is like, and now Josh, and now Zach, and now
I'm
Josh.
excited to hear more about Jubilee. It's such a neat machine.
So yeah, what happened with Jubilee? So that was actually like grad school work, or that was just something that like because you said it's still going. So like, is that a project that was like your thesis, or how did that all go?
Yeah, so I think kind of the way I've been trying to organize my life over the last, I don't know, I guess ever since I like left undergrad, it was kind of, can I find ways of kind of shoehorning projects I'm secretly interested in into like the work that I do? Don't tell my employer that.
No. That
Um,
is actually that's the life goal right there. That's
but yeah, I think that's
paid to
so
learn.
exactly. Yeah, so I have this huge list of projects that I want to do, and 3D printer was one, and head changing like 3D printer was another one. And so I figured, okay, like let's like, can I pitch this as like a grad school project? So the first month that I was there, my professor, Prof. Nadia, was interested in this idea of fabricatable machines, and so this kind of ecosystem where you could take a machine and build it from very readily available constituent resources. And for me, I said, "This is awesome. Can I build a tool changing a CNC machine?" And she said, "Sure." And so I kind of took that first year as an opportunity to kind of start unpacking this multi-headed 3D printer that I had in kind of that I've been interested in for a while. Turn that into something with teeth over the course of the next year. And that's kind of what happened. Is I started pouring like a lot of time into SolidWorks and then trying to understand, okay, this fabricatability idea is we want to be able to kind of throw a design out the door in a way that somebody else can reproduce the project from kind of rudimentary tools, rudimentary techniques, kind of like you want to like you have a Lego set and all these parts come together and they fit together in certain ways. That was kind of also baked into this idea of fabricatability, where I could take a kind of the components were supposed to only go together in certain ways, and it was the correct way.
Yeah. I remember that. So like I remember your demo. I think you had brought it to one of the other conferences where we saw each other. And I remember you showed me this like the head that goes onto the 3D printer, the
Yes,
the
I do
tool changer.
remember that.
Yeah, and it's almost like a true like zeroed kind of thing, right? It's almost like known in space where it is because of how it all lines up. What is the mechanism for that?
Yeah, yeah. So that's called a kinematic coupling. It turns out that, where I work now, which involves a bunch of optics. Like these things are like, they're a dime a dozen. They're all over the place. But at the time, I had never seen them before. And so, kind of the thing that this does is it's a way of taking two parts and joining them together such that they only fit one way. And it's a repeatable mechanism. So you can take these parts apart and then you put them back together and take them apart and put them back together. And the physical dimensions of both of them are such that they only fit together one way. The nice thing about this is that the construction of these two plates to form this coupling is very, very simple. You can do it with dowel pins and basically steel BBs. And the idea is that this is built baked off of this concept or this like line of mechanical engineering called the method of exact constraint, which there's this cute little blue book that you can buy about it. And it's kind of like free body diagrams, but in reverse, where you want to take a physical thing and you want to pinpoint it, you want it to fix it in space such that it doesn't move or it only moves along certain degrees of freedom. And the way you do this with the method of exact constraint is you use the minimum number of constraints to constrain every degree of freedom. And so if you think about a physical object that's floating in space, there's 6 degrees of freedom there. There's 3 rotation and there's 3 translation. If you want it to only have 5, what you do is you take like a pin and you put a pin through this object in space, and suddenly it can only move along this pin. Or it can't translate. It can only move. It can only rotate now, and so you cut down degrees of freedom this way. So that's what the coupling does, is that it uses the minimum number of points basically to constrain these two plates together. And if you do that, it turns out you can build a really cheap locking mechanism that's really, really accurate. And that ends up being really good for heads or in tools that you need to detach and put back over and over again on a machine.
Yeah, like repeatability. Whenever I see those like monster tool changers, the one thing I always notice is like that crazy shape. I'm thinking of like the Haas machines that are out there, like the crazy shape of the tool change heads, and like that. That is part of why they're so expensive, also because it's a captive system. But like, yeah, but like that shape is really important, right?
Absolutely. Yeah. And it's I think the way they do it is slightly different, where
Mm-hmm.
they're using like they're like two conical sections that they're attaching together, and they put a lot of pressure on the tool. They pull it up with a bunch of pressure, but it's the same idea. It's like you want to
Yeah.
be able to, you want this thing to only spin. That's your end effector. You don't want it to move in X and Y except for unless the piece that's holding onto it is moving in X and Y
Mm.
or Z. And so you apply this force into this cone that just prevents it from moving.
Hmm.
Josh,
Yeah, that's
hearing you talk about kinematic couplings makes me think of a company I came across in school called Baltec, BAL-TEC, which is just a really fascinating tiny company that basically sells all of the components for making kinematic couplings. And some of them are just enormous. Like they have these canoe couplings that are designed to handle massive loads without deforming. I don't know if you've come across them, but the website is the delight. It's just a delight.
I think I did eventually find like I like landed on their website at one point, because I actually had this problem, which is like, okay, people want to build my machine. It has a kinematic coupling on it. How do we get them to? We either have to make the coupling out of rudimentary parts, or we need a way to have, or need to go mass produce like a couple of these specific components. And originally, I was going to have people make these out of steel BBs, but eventually, what I did is I went to this vendor on Alibaba and I asked them to manufacture like a couple thousand
yeah.
8 millimeter steel ball bearings with an M3 threaded hole drilled halfway into them. And
Oh
so
wow.
that was how I kind of distilled this like precision out to the world without them having to do this on their own.
Yeah.
So that like the whole
And now you've
fabricatability
captured the
thing.
market, right? You're the only one selling these M3
Okay, so it turns
threaded
out
ball bearings.
the original way I actually had people do this is I looked for this part, like kind of in the back of my head. There's this like wish list of parts that I wished existed, and this 8 millimeter ball with a threaded hole drilled into it. That was on my like wish list. If only I had that, then I could build the rest of this machine. And it turns out there was someone on eBay who, I don't know if you're familiar with kind of stop motion. There's a whole ecosystem of people who will build puppets for stop
Hmm.
motion. And what they do is they use these ball and socket armatures that are these
Oh,
metal
wow.
components that are essentially exactly what I wanted. And so it just so happened that they were selling an M3 threaded 8mm steel ball.
Oh, man.
So the original bill of materials actually pointed you to this one-off eBay website that said, hey, go get a 25 pack of
That's
these.
amazing.
I wish I could distill the feeling of finding, because I can actually like have some memory recall of like a similar, obviously different scenario, similar sensation of like finding that part. There is like some kind of dopamine hit that is just like, if I could distill that, I could sell it on the streets, man. Like it would go for good money. Like the amount of dopamine you get from finding that perfect part. Oh, it's good stuff.
I totally agree. And sometimes it's like if I could only know the name of the part.
Yeah. Oh my gosh.
I have
Yeah.
this like this kind of comes up in the Hackaday articles that I was more periodic about writing, this idea of the vocabulary of parts,
Mm-hmm. Yep.
where I would kind of show people these like, here's this cool new part that's like a mechanical component, and here's a normal way to use it, and here's a way you can kind of use it in a non-conventional way to do something other than what it was supposed to do. But it's like, here's the name of this part, so you can go look it up, and you can kind of see it being used in different ways. And now it's
Totally.
like it's part of the grammar of your kind of nuts and bolts that you use to design with.
Totally. Yeah. Mental library is so important. And like immediate recall too, because it's like, if you think about being tongue tied in that same way of vocabulary, you might actually go down the wrong path, and you'd be like, oh well, I don't know the proper way to join these two pieces together, but I could maybe 3D print a jig to do everything, and you spend 4 weeks doing the jig, and then you find out there was a way easier way to do it. So like that kind of sounds like what both of you were kind of in these grad programs for as well, like the putting of things together, right? Like the making of things. That's a very simplistic distillation of what you guys did, but you now have that vocabulary in your lives because of the grad school that you did, and the work you've been doing still.
Yeah, I think we need like a mechanical equivalent of DigiKey parametric search. We
Hmm.
have like
Not McMaster.
yeah, well, McMaster's all right, and you
Yeah.
have Misumi, which gets you pretty close, I think. But
Misumi.
yeah, Misumi's kind of a more customized. You can often get things that are semi machined to order. So like I would buy these hardened half dome dowel pins that I would use these for making little kinematic couplings, and it would be a 4 millimeter OD with a half sphere machined onto it, and then it would have a 3 millimeter OD pin sticking off the bottom of it. But you could size that to order, so you could tell them what length and what
Oh
diameter
wow.
you wanted, and it wasn't
Yeah.
monumentally expensive either. So you could and the lead times were relatively short, and you could buy it in hardened steel and so forth. So they have, Misumi will like periodically add a new configurable, like configure to order mechanical part like that.
Hmm.
But it's still pretty expensive, and it's still very much like single sourced, right? And it still takes a while. It's not ideal, and it's limited. I mean, like the threaded 8 millimeter ball like that Josh was talking about is not a Misumi part, so there's nothing close to
Yeah.
it on the
Right.
site.
Yeah. Well, so it's interesting that Joshua's project is ongoing, right? It's a open source project, and it sounds like people are building it in the same way. Like Zach, you mentioned you were continuing work on someone else's project, and like that's kind of just how a lot of these labs go. I have a feeling for you build on other people's research, and because generally that's what research is. But like Joshua, what is the kind of what is the long term for this for the Jubilee project?
Oh yeah, I think what I wanted was I wanted to be a reference of all the like best practices of the time for building kind of precision XYZ stages with head changers with rudimentary parts and processes. So it's really like if you go to scroll to the bottom of a data sheet and you look up the reference design section where they have like here's the ASIC that they're selling you, and here's like a bunch of applications that you might be able to use it for. So I wanted Jubilee to be this reference for precision motion. If I just wanted a platform, and I wasn't necessarily going to go buy one, how could I build one without having to think about the design of it?
But are people still building it as well? Like, is it kind of an ongoing like is it an ongoing thing for you? Is it an ongoing thing for people building it? What is like what's the active piece of it versus kind of the reference piece, like you mentioned?
Yeah, I think it's on and off. I think it really depends on how much time I have to devote to it now that I'm actually like working full time, and it's become much harder to find spare time. But yes, the short answer is yes. I think there's right now what I did is I worked with a commercial vendor called Philistruder, and we created a kit for one of the latest revisions of the kind of like the latest release on GitHub of Jubilee is something that you can go out and go buy as a kit of parts. And it's basically
Nice.
someone went
Okay.
down the bill of materials and said, "Hey, let's put this all into a box." So that's one thing. There's a Discord community right now which has grown over to a little over 2,000 people,
Wow.
but I think most
Whoa.
of that growth happened in like the first like year and a half to 2 years. And now like I know there's about 150 people who have built one in the wild that they kind of exist in someone's living room somewhere like all over the world, which is really cool.
That's really cool.
But as far as like the machine, the core machine development and or the tool development for the heads that go onto it, I've done very little in let's say like the last 6 months while I've been kind of onboarding to a new job. But it will pick up again.
Got it. Okay. So, but Jubilee lives on. That's great. That's great.
I'm interested to hear if there's any strange or esoteric community developed heads that have come out of it. Because that was I had my
Yeah.
colleague Jake Reed, who Joshua, and I think you know at CBA is also doing tool changing open source fabricatable machines, and I think that's always been the thing he's talked about is like wanting to develop a community of people that make heads for the machine, right? So
Yeah, that's the
have you
dream.
seen any interesting things come out of your Discord community that are kind of like the pancake batter syringe for CNC breakfast production, or like any really weird ones like that?
So the short answer is I've seen a bunch of people do some really fun things, but it's not necessarily making heads. It's not to say people have made some cool heads. And I also made some fun heads where we collaborated with a lab and we ended up doing a sonicator head, which is
Oh.
like an ultrasonic stainless steel probe
Hmm.
that people in the sciences will use it to kind of break down cell walls for DNA. And we basically just turned Jubilee into a kind of a liquid handling motion platform that was
Hmm.
scriptable with Python. But as far as what other people have done, I think a lot of it, the way I've seen people mostly use the platform is a starting point for them to put modifications on top of what's already there. And I think that's not a bad thing. You should absolutely do that. Use this as a jumping off point that I can vouch for, and then kind of make your own tweaks to it. So I've seen mainly the majority of what I've seen in terms of heads is more printer
Mm.
heads, more better printer heads.
Yep. Yep. Yeah. I mean, that is. I mean, if people are coming into the 3D printing space, I'd say the majority of them are going to try and do 3D printing, right? But a generic, 3-axis machine is also very useful in a lot of contexts. So I could imagine, like the tappy style robots and things like that could also. There are a lot of uses of of a device moving in 3D space. So we just got to wait for the concrete pouring, specially lined Jubilee head, sized up to mega scale, right?
Oh my goodness. I mean, yeah. And I think for people, it's really for some people it was like their first time wetting their lips on kind of all these precision components and kind of knowing that there was a set of instructions that would take you from start to finish. And like that's something I want to give people too. Is like give
Yeah,
them a good first experience putting together parts. Like get that feeling in their hands.
totally. Zach, your work has also continued on. Is that yeah? I'm not sure about on the academic side as well. It's like you didn't spin yours out to open source, but yours is still out there. I'm guessing.
Yeah, the work that I did previously is still floating around, but I think it hasn't really been picked up as much. I'm hoping maybe someday, periodically, if you look in like the last 80 years, people have wanted to build little neuron simulators, and I'm hoping when I decided to build mine, I looked all the way back. I mean, the first one was Otto Schmidt's PhD thesis when he created the Schmidt trigger. He was building a neuron simulator.
Oh,
Yeah,
really?
and
Oh,
it's
wow.
in the electricity museum, the Buchan Electricity Museum in Minneapolis. I got to look at it when I lived there.
That's cool.
But like since then, people have done it. They've tried to make these simulators. So I'm hoping maybe in the future someone stumbles across it and takes our lessons.
Yeah. Yeah, totally. I was actually talking about the grad school stuff too,
Oh
though.
yeah.
The
So
not
yeah,
the
one of the projects I've been working on is definitely ongoing. So we're not to like dive into a rabbit hole on solid state NMR, but basically you need to average out, these anisotropic spin modes that when you do NMR on a liquid sample, you take advantage of the molecules kind of randomly bouncing about, and that averages out these.
What is NMR? Sorry, I didn't ask that. I didn't
Oh,
think up front.
nuclear magnetic resonance. So kind of
Aha,
similar to
okay.
MRI, like you have a giant magnet, but instead of imaging, you're trying to get molecular structure. And with solids, you can't take advantage of the liquid phase to like randomly bounce molecules around. So for reasons again that not only will I not get into, but also I'm not an NMR person, so I can't really explain. I'm just the fabricator. You have to put the sample in a tiny tube and spin it very quickly and at a very specific angle with respect to the magnetic field. So basically, the faster you can spin a tiny sample in a tiny tube, the better your resolution and the faster your samples get acquired.
Mm.
So now the tubes, as you spin a tube faster, it tends to explode. So you make the tube smaller. So the tubes used to be like 10 millimeters in diameter, and now they're 0.7 millimeters in diameter. So the diameter of pencil lead, and their inner diameter is half a millimeter, and they're made out of like a yttria stabilized zirconia, which is just a really tough ceramic material. And they cost like $2,000, for this 4.5 millimeter tube, and it spins at about 7 million RPM. And it does that in the bottom of like a,
Wow.
Back up. 7 million RPM.
Yeah, well, so they talk about it. It's so funny.
How did they not come up with a different unit at that point?
They did. They talk about it like in NMR language. They talk about it in kilohertz. So they're like, oh, it's 111 kilohertz rotor, and you're like, oh, that's not very fast. And like, well, no, it's the tachometer reading is 111 kilohertz. So it's so we would always at our so we did this collaboration with the Francis Bitter Magnet Lab at MIT, and like they're all the NMR people, and they talk about kilohertz, and we're like, no, we have to think about it as RPM because otherwise it doesn't sound as interesting. And then you have to do that like in the bore of a 15 plus Tesla magnet, so the more powerful the magnetic field as well, the higher the resolution and the faster the acquisition.
And what does one measure with this? Like what goes into a tiny little pencil lead tube?
Kind of any like organic or inorganic solid that you're trying to figure out the molecular structure of. So they were using it for Alzheimer's plaque and like amyloids and like trying to understand the very complex molecular structure of interesting molecules.
So like back calculating basically what's in there and how they're all hooked together.
Yeah, right. You can get this very, very complicated high resolution spectrum, and then you put it you run it through a lot of software, and you're able to derive what the actual like ball and stick model of the molecule is. It's what feeds into very complex ball and stick models that you'd make in your chemistry class.
Yeah. Lots of balls, lots of sticks. Yep. Yeah. But you know what? When you start getting like 8 millimeter balls with like an M3 thread in it, and then you use that to put all these molecules together, it's like so
that would be a cool, cool chemistry set. So we got to this point where the tubes were starting to explode, and my PI had gone out to like a PI meet and greet and met the PI principal investigator, the person that runs the lab, had met the PI of the magnet lab who complained about his tubes exploding. And my boss was like, well, we figured out how to machine diamonds with our laser. So let's try to make tubes out of diamond because diamond is really strong. So why not? Yeah. Like let's just throw everything we got at it. Like,
they're not the good didiamonds. These aren't finger diamonds. These
these are
diamonds.
Chemical vapor deposition grown diamonds, and you can buy CVD diamond for like $10 per cubic millimeter roughly, and you're limited in size. Bingo. But like it's for if you're trying to make a tiny tube out of it, it's actually not that expensive. So I got involved because we needed to like machine a tiny tube out of diamond. So we had a laser micro machining system. So I built a lathe for it that would allow you to machine the OD of the tube and then flip it up so you could machine the ID at the same time and maintain concentricity and all that.
It's like the exact opposite of like Colin Furze just keeps like bigger and bigger stuff, and you're just going smaller and smaller.
Right. No, exactly. Lathe, right. And my machine like barely. I mean, we got it to work, and we're submitting it for publication, and we're excited because we were like able to spin a tiny diamond tube to 7 million RPM and get like the first NMR spectrum from a diamond tube, which is big. I mean, that's like cool. Diamond has advantages because it's transparent to microwaves. So you can do what's called dynamic nuclear polarization, where you couple in, 100 gigahertz microwaves from a gyrotron and are able, again, because NMR things, like you're able to increase the resolution and decrease the sample acquisition time. So using diamond is great because it's effectively transparent to radiation at that frequency range.
Sometimes you guys sound so normal, and then sometimes you guys to pull the stuff out like this, and I'm just like, wait, what?
Well, so
that's crazy. That's really cool.
So it's interesting, but like the project is like the method that I developed was like, okay, we need to make this precision machine that we can like flip, because we needed to maintain like micron concentricity between IDs and ODs and micron taper between the two ends. So like my machine was
I feel like we said ID and OD a bunch as well. Inner diameter, outer diameter.
Outer diameter. That's a TLA, a 2-letter acronym, not to be confused with a TLA, a 3-letter acronym.
That's right.
Yeah, so like my machine was basically like kinematic couplings and micro adjusters. So the part I discovered in grad school was the precision micro adjuster, which is basically like a little brass tube that has like 50 micron pitch ID threads in it, and it's got a matching slug that has like a 3 millimeter hardened steel ball on the end of it. So every turn you turn the slug, it advances by 50 microns. So you can use that to make like, you embed those in structures and have them made up with hardened kinematic couplings, and they can like, you can make precision micron adjustable machines. So my way of building precision machines was like sprinkle micro adjusters all around it, and then hang a laser displacement sensor on our machine gantry and use it to like tram things in and adjust them. And it worked really well. It just like couldn't handle any forces, and it was fussy to align. But
sure,
the ongoing work is like the much more talented people that followed me that like know a lot about how to design precision machines that are making it far more repeatable and far more robust, and like getting our concentricity from 8 or 9 microns to like 1 or 2 microns. So yeah, it's been interesting. I came into that project pretty early on and like kind of got the first spectrum, but now there's people working on it that are going to make it really work well, which is exciting.
That's cool. That is really cool. Okay, so I was also interested. So both of you have given us very positive sounding experiences so far. Let's get some bad stuff. What's the bad stuff, guys? Time to dish.
I feel like when I think about grad school, I feel like you go into like a situation in life and you like crank the contrast ratio all the way up. So at least for me, like you took all of these things that were sort of good or sort of bad, and you were just like, this is now fucking amazing. Like I have a wire EDM, I got like an SEM, I got all this other stuff, but like also like I'm not making a lot of money. Like, and Cambridge is really expensive.
I should also say, before we dive too deep in here, I told my wife that we were going to be talking about this stuff, and she's like, Chris, you have proclivity to be a little anti-education, so I don't want to sound too anti-education in my responses here. I just want to like preface this because I've been accused by my wife and others of being that way in the past. So I'm not anti-education, because the stuff that you both described, I don't know if you would have been able to do that stuff other places, and that was through educational institutions. Yeah. I think we're talking about the institutional piece of it, though. That's really the downside from my perspective. Sorry to cut you off, Zach.
Keep going. No, you're totally contrast. Good. Yeah, because there's just like, there's dramatically negative parts to it too. You depending on where you're working, you have varying degrees of success, like deciding what you're going to work on, right? So in some cases, if you really want to work on a thing, like you have to find the time yourself to do it. And that can be really hard when you have other deadlines or you have different pressures. And I think that I know, and Joshua, I'm sure you'll speak to this more, but like where your advisor is in their career is an enormous factor. I was working for someone who had tenure for 20 years, and like I didn't really have a huge amount of publication pressure, but there was pressure to do really interesting, novel, crazy, out there things to like keep us relevant, and that can be hard to balance versus, wanting to work on things that are more modest, but, are maybe more quote unquote incremental, but like still worthwhile,
I like throwing around the word dignified. It's dignified work.
It is dignified work?
No, incremental is dignified.
Oh yeah, incremental. Yeah, right. I my old boss used to always talk about like R&D Some places are big R, little d. Some places are little r, big D. And the place I used to work was little r, big D because it was like, it was all just development. It was just doing more of the same thing, but you still had to, there was a little research pieces in it, but it was nothing like crazy there. It sounds like in the grad school stuff, it's big R, little d for sure.
I think it really depends.
Mm.
Because I mean, yeah, I think I think that your grad school experience can be highly variable. Because I think I would argue that before, when I was still working, there was quite a bit of R and D, and so I was very fortunate that I got to be able to kind of pick and choose, kind of depending on what was not on fire, which part I would go work on. So for context, before grad school, I was working at a synthetic biology company that was started off as a startup. So I think it was like employee number 24, and I was kind of the human who would write software for hardware and occasionally spin PCBAs for the instruments that were going into the factory. And so I think because there were fewer instruments when I started versus when I left, and we got to have a lot of a say in what instrument was going to be the next thing that we wanted to build and put into the factory.
Yeah. Yeah, machine design is ripe for research, I feel like, just because it's like you got to figure out so many things about each piece, and then you also have to make it stable enough to be in a factory setting.
Totally. And I think that was the really fun part about it, is that first there was no instrument, and then there was something that worked once, and then there was something that eventually we had to get it working
Yeah.
24/7.
Yep. Yep.
And I think that was super fun. And I think honestly, a lot of that translated over into kind of the work I put into Jubilee, where I got it
Mm.
working once, and I think people were really excited. And I was like, "Whoa! Like this only worked once. Like this is a head changer, and we need to be able to take the head off, on and off, like thousands of times per operation. Like if you want to print a multi-headed part, that could be like 300 tool changes, and it needs to work perfectly every single time. So I had to set up a bunch of like cycle testing that I would run late at night, and then eventually, like, the 250th time something would break, and eventually I had to get out the camera and figure out, okay, where is this breaking, and record things so that I could go back in time and see what was going on.
Your demonstration at,
Mm.
I think it. I'm trying to remember when you brought Jubilee and I first saw it. It might have been at a Hackaday conference, or it could have been. Might have been at Teardown actually. But seeing it print that interlocking dinosaur, where every layer, or like every other link, was a different color, so it would just have to do head changes. Like every single layer was. I had never seen anything like that. That was amazing.
Yeah, it's dialed in. Yeah, that's really cool.
I think so. In a way, I think I got really lucky because when I was interested in this project at the same time as I would say the whole world's, like in the hobbyist world, their appetite was also whetted because people were talking about CNC, like tool changers, being the next evolution in 3D printers. And at the time, there was a company, E3D, it's still around. It's a wonderful group of people that was starting to come out with a beta version of their own tool changer at the time. And I think what ended up happening is that my work on Jubilee and their work on the E3D tool changer, it was always like intertwined. Like we couldn't like ignore the other. We couldn't, like, neither of us could ignore each other. In fact, I saw the first kinematic coupling on a Twitter post that they had posted in like an earlier version of their machine. And so that was kind of the aha moment where I was like, okay, I could make this out of rudimentary parts. But I think part of that project's success was because a lot of people, I think we benefited from a lot of people knowing about this like tool changer concept and being really excited about it. And I think that's still kind of the case too, because one of the bigger 3D printer vendors, Prusa, is still supposed to come out with a 3D printer that has a head changer on it, so you can switch between, I think, like 6 colors.
Oh,
And that's supposed to
Oh,
be
wow.
that's slated to come out like later this year, if
noted.
not early next year.
Wow, that's awesome.
That's cool. So Joshua, one of the things you said there is like the kind of the late night testing. That was kind of like what Zach was talking about as well.
Hmm.
And what that kind of inspires in my head is kind of that you had said like what did you say? It was like grateful work or something like that. But
Dignified.
Oh, dignified,
dignified work.
yeah.
But the reason that kind of got me is because like it does feel like a lot of I like my vision of grad school, and I did not go to grad school, is that you kind of have a lot of grind as well, and it kind of sounds like that late night testing as well is kind of there. Was there generally that piece? Was that part of your experience as well, of like just kind of drudgery, or is it not really that?
I think yes and no in different ways. So
Okay.
let's say during the early testing, when I think kind of my PI wanted me to move on, it worked once, like ship it, like send it out to the world. For me, I was very afraid of releasing everything as open source too early, because because I knew what people wanted to do with it. They wanted to put a 3D printer head on it, and if you drop your 3D printer head, and they want to run it overnight, and if you drop this in the middle of the night, it's a huge fire hazard. So in a way, like the diligence of like coming into lab late at night and running a bunch of tests over and over and over, and then redoing the design a few times until it worked, that was partly because I was afraid that people were going to take the design, try to build it, and then like have a fire in their house. So that's
Oh
so
yeah.
that grind did happen in the beginning. And then I think the next
And when
grind
you
came
say
out
when you say late night in the lab, you were there like monitoring. It wasn't like you set it and forget it. It was like you were there watching it.
in the beginning. I did not set it and walk away from it.
Yeah.
Am I
Okay.
supposed to admit that?
I mean,
But I did do that later. Okay, so I did do that later, where I would, fire it up and then come back the next day. But at the beginning, it just wasn't good enough. It was not reliable enough. Where I'd run it for 10 minutes and it might be fine, and then I'd run it for an hour and then something would break. Or after running it for 6 hours, like only after the 6th hour would something like melt finally, and then you had to figure out what fell apart. So there certainly was a grind there. I think the other grind came from once everything did start to work pretty consistently. It was just a matter of churning out instructions, and this is something that like I actually really enjoy, but it took a while to get faster at it, which is kind of so the thing that makes I think Jubilee really special is that it's an XYZ motion platform, it's open source, but there's like 120 something pages of step-by-step instructions. They're visual, they look like IKEA instructions, they're colored. Every page has like the list of all the parts you're going to need and how many, and there's very few words. It's mostly pictures, and that's on purpose so that you don't have to spend a lot of your time reading. You can spend most of your time putting stuff together. And so what I basically had to do was in CAD create a view for every single picture of every single kind of diagram of every single like part going into different places, and that was definitely a bit of a
you know that
grind.
IKEA has like an army of people doing those crazy directions too. So like you're basically doing the work of an army.
And I wish I had those people.
Yeah.
And
Right.
that was
Yeah.
kind of, I think, one of the biggest drawbacks of the project. But it's not something I couldn't have worked around it, because I did all of my work in SolidWorks, and the issue there is that it costs money to have a SolidWorks license.
Yeah.
If I could have had someone else make instructions for me, absolutely, yeah, I totally would have said,
Yeah.
please, like break it down step by step like this. We can review it, but it's not something everyone has access to. This is partly like my hope for things like FreeCAD, is that in the future, as things mature in that world of open source CAD work, having like instructions as like a first class feature, I think would be
Mm.
phenomenal for being able to share mechanical designs and have other people reproduce them. Because I don't know, in my mind, like
Yeah.
the
I
design
don't
has
think
to be.
FreeCAD's there yet though. Sorry.
I know, but I
I've
think
been in it for a
we get
couple
there.
days actually. It's I'm getting better, but it's on the individual, unfortunately.
Yeah. Yeah, so I think in the future, we could get there, and that's, like, the future that I want, where the
Yeah.
idea of, someone gives you the design and, like, what's the design? Like, is it your CAD file? And the answer
Mm.
is, well, yes, it's the CAD file, but it's also the instructions of how to put it together. It's the CAD file, it's the wiring diagram, and then it's a bunch of step-by-step instructions.
Mm.
Because there's some people who can build things from just opening up the CAD model, but the problem is like that's practically speaking really hard to do, because you can put something together and then realize that you're missing parts in the inside, and you have to take the whole thing apart before you can stick those parts in. So I really do think that the design, if I like waving my air quotes around for design, I think that includes like the procedure to assemble it.
Just making those instructions though, like I just imagine you have to think about like when do you when do you decide to still use a screenshot from a CAD cutaway that is not perfectly
Mhm.
accurate, but like maybe it's not
Yeah.
perfectly accurate in a way that doesn't impact at all like the assembly instructions or whatever, or maybe you're
Oh
like
my
have the luxury of
oh yeah.
making the instructions after everything's locked in. But I know when I made instructions for things, there were always parts of it that were like, well, that's not quite up to date, but it doesn't really matter, and that's really stressful.
No,
That's
no,
really
you're
stressful.
you're totally right. And I think for me, like what I realized is that the more true to real life the CAD model was, if the CAD model was a perfect one-to-one representation, perfect in quotes, but if it had all the constituent components or representative components for it, that was the best you could be. Because the problem is that you change the design a little bit, you're probably going to first, in order to do that, since most of these parts are 3D printed, in order to really change the design, you're probably going to change the model. And
Yes.
so if the model is inside of a bigger assembly, if you do the instructions right, then what happens is that you update the model and then you reopen the instructions and everything resizes and automatically changes again and
Mhm.
reaccommodates the new view. And so you do a little bit of extra work by coming up with all these views and like assuming that you actually tie them correctly into the original assembly. They auto update every time you change
See,
something.
because you did it
And
the
once
right
I
way.
figured that out,
Yeah, you didn't do
Yeah.
screenshots. I always just did screenshots,
Right.
which is
Screenshots are
the
like
wrong
frozen
way
in
to do it.
time.
Yeah.
Yeah. It's like the difference of like having like downloading the zip versus like, cloning the Git
Right.
repo,
Right.
right? That's
yeah,
like
yeah.
yeah.
I think this was really a point of contention, because I think the thing that I couldn't do, that I wasn't willing to do, was do like video, because I think same thing with pictures. I think I realized that like if you take a picture of something, it's exactly what happened. Like what you said, it's a moment in time. And the thing is that like you need good lighting for that picture. You need a good workbench for that picture. You need to have like a setup where you can go to and like take the whole thing apart. And that's like a whole lot of effort.
And if you are willing to redo it later, you need to replicate the look and feel each time as well.
Exactly.
Mhm.
That's
Yeah.
exactly
Yeah.
it. And so I realized that if you had all of this captured virtually as best as possible, then you just push a few buttons, change the model, and everything downstream just updates, which is awesome.
There's a lot of cost to doing that though, I think, right? To have a perfect model and have all the views. So
I think there's a ton of upfront cost, but I think at
Yeah.
the end of the day, what I was reminding myself of was, before I was in grad school, I was working, and for the most part, people, they had things down to the nut and the bolt. And the
yeah.
benefit of doing that is that you just right click and export a bill of materials, and it's perfect as long as your model has everything that's there.
Yeah. And so so both of you were working prior to going to grad school, and
Yeah.
then you were, you said something about. I also didn't listen to the episode, so I should have done that beforehand. But you said something about you were both excited. I remember that piece. If you were gonna talk to your former selves, what would you say? So if you had a 3 year, an only 3 year ago time machine, what would you have told those folks?
Yeah, I would say like trust yourself and have fun, and it goes really quickly. But I would certainly never like try to convince myself not to do it. I mean, I have
No, I wouldn't have expected that. Yeah, yeah. What would you have warned yourself about, though? I guess this is the real thing. Like, you're going to do it still, right? You want to be at the 3 year later mark.
yeah.
But what would you have
I think I would
warned
say
yourselves about?
like there's just it's just like a minefield of rabbit holes, right? And like there's gold at the bottom of some of them, so you like have to go down some of the rabbit holes, but a lot of them are just you can just keep digging forever. So like you need to figure out really early on how to evaluate rabbit holes and like how to decide where to spend your
Mm,
time, because your time is limited. And like really, I mean, being there for just a few years, like you need to like set the direction of what you're doing pretty early on. I mean, there's really a grace period in some ways where like you start and you have more freedom at the very beginning, and like you need to really quickly evaluate what the focus is going to be so that you can start digging into it. And that's really, I mean, it's
yeah.
hard and it's scary, but like you have to be able to do that and commit to it.
Oof.
Joshua, what would you tell your younger self? Again, yeah, I think we should assume that you're both going to do it because you want to be where you are now, and also if you have a 3 year ago time machine, you don't want to change the present. You just want to.
Yeah.
Come on, rules apply here.
That's tricky, because I think that the 3 year mark was really good. The first year I think was really good, and then I think after that
Oh, sorry. I was sorry. I was keying on 3 years. I'm saying beginning of your. I forgot yours is maybe a little longer.
oh
Sorry.
sure, okay, the
Yeah.
beginning. Yeah, I think maybe I would tell myself like, don't forget why you're there, is the first
Mm,
thing, and then if it's not working for you, like just keep like for don't forget to advocate for yourself.
mm. Yep.
And you yeah, I think it's don't forget to advocate for yourself. Like you had reasons why you wanted to be there. Like, are those
Got it.
still or do those still hold true? Is this
Uh-huh.
kind of what you wanted? So just like, or I would remind myself to reevaluate.
Okay, that's good. Yeah. So one thing that again, my outside perspective and you two, but then also my other friends that have gone to grad school, it does seem like there's a lot of things you can't control, right? You can't control how your relationship with other grad students might go, how who you have to manage if you're managing, younger people, or, all of the things that go that way. It seems like there's kind of just like tidal forces that are pushing and pulling you a lot of different ways. And you both kind of sound like it's like that is tough to break out of. I mostly think about tropes as well, of like having to TA classes or TA labs and stuff like that as a grad student as well. Just things that are the mechanics of being in a larger program.
Yeah, I mean, I think TAing is often like some people you talk to, and TAing is like the drag they have to do for the first year or two or three of their program, and even that, I think, let yourself be surprised by it. I don't know. TAing was one of my favorite parts of school. Like Neil teaches a class called How to Make Almost Anything, and like being a TA for that class was just one of my favorite parts of being at CBA. Was like seeing all these people come in with wildly ambitious, poorly scoped ideas, and like helping them figure out how they can actually make them using machines they didn't know existed when they started the semester.
That might be one of the most, that's one of the classes that I've seen that I've been most jealous of, for people that get to go take that. It seems like it's really cool.
It was fun.
Oh yeah, I remember stumbling on that like the websites of people's project websites, and being like, "Oh my goodness, you guys get to do this in school?"
Yeah, it's that. It is that. Yeah. There's
That's
like
cool.
a funny. You hang out with your advisor long enough, and you learn their isms. But like, there's a Neil ism that I think rings true, which is "Don't suffer in silence." He would tell us that, but remember that. Like, to Joshua's point, like, advocate for yourself, but make sure you speak up.
What does that look like too? Because I mean, like, I could also imagine like someone taking that advice and being like complaining to their advisor, but then getting smacked down because of that, right? Versus like, talking to your peers, talking to people outside. Like, what does that look like to advocate for oneself?
Yeah, I mean, that's one of the challenges, is like you don't always have that many avenues. Like, it's really depending on your program. Like, the buck kind of stops with your advisor, but depending on the situation, like my program was very lab centric, so it was like you apply to be in a certain research group and you get accepted into that research group, and not into like a general class of people joining like the chemistry department or something. But in a lot of programs, you'll have a committee of other people on faculty that might be the ones responsible for deciding when you're allowed to defend, and
Oh yeah. Yep.
so you can get folks like that involved. It's all just complicated because the power structure is that you have no power and they have all the power, and you don't want to go behind your advisors back. So it's hard. Like, it's hard.
Yeah. A friend is working in academia now, and they told me about it's just like it's like a true pyramid scheme, right? Like, it's like there is the person at the top, and it's by definition they're at the top because they are, they get all the money, and they drive all the research decisions and all the other stuff, and that works fine most of the time until like you disagree with the top. Like, that is where it could potentially be problematic, and it's not necessarily wrong. They might not be wrong in the global sense, but in terms of like what you need out of the program, I can imagine that would be potentially problematic. Of like, hey, I'd like to graduate and move on with my life. Can I do that? And they're like, no, you can't do that yet. Oh,
Right.
I've struck Joshua and Zach dumb, or their connections have dropped as I maybe hit a point there. So I will move on from that.
It's hard to talk about.
Oh no, no.
It's just it's so complicated, and it's so I don't know, Joshua. You certainly don't have to comment, but like, I know I just have a lot of emotion tied up in it, and it's not, that doesn't mean it's bad to talk about, but it's a lot, right? It's you go to a place that's like, that's your life, whether or not, like, I think I gave the MIT like 2 all-nighters, which is like probably way on the low end for grad school, but so it wasn't my life literally like sleeping in the lab all the time, but it certainly is, like, emotionally and mentally, it's like that is what you are and who you are when you're there. Yeah, it's your whole
it's your whole world,
exactly.
Right? I mean, like, that's what you can't have a whole other world, right? At the same time, I'd imagine.
Yeah, I really didn't do anything that wasn't related to lab, other than like take pictures of birds occasionally. which was fun, you know. Like, you know,
That's just a COVID
yeah,
thing though, too,
right,
right?
right,
The COVID thing,
right.
right? Hey,
Oh, I didn't think about that. Yeah, no, I think Zach, what you said checks out. I think it's actually interesting too because I think I made the right choice, which is to depart with a master's. I made it at like the right time because it's been it's been about a year since I worked on Jubilee in like great detail, and I think I what I realized after I left the lab is my original like I think I've kind of thought of myself as someone who's always hungry for projects and projecting and shoehorning some learning experience into like into my garage late at night. And I realized that I tried to do that after grad school and I couldn't do it. And it's been about a
Yeah,
year since
huh.
I've tried to like pick up a project and make it fun
yeah,
again. And I think that's like the big cost I think for me, which is this part of myself that was very near and dear to me. I have been in like almost completely unable to connect with it again, which
Huh.
and
Which
it's like
is it just the identity piece, or is it the actual like just the kinetic energy to get started on a new project just for yourself?
oh, it's tricky. I think part of it is that, like, in a way, I feel like this part of who I am was like weaponized
hmm
and used in
yes.
the name
Oh
of
my
like
god,
something
yeah.
else.
I like that. Yeah, so you guys
Ooh,
are like you're like the superheroes, right? I mean,
yeah,
it is, right? You're going to basically superhero training for this, this skill, but then they point it at, not they, that's too singular, right? It's academia. You're pointing it at, basically trying to use it to make money off of it, right? In uh, research dollars or whatever, like basically really focusing it down onto a single point. I always talk to people about like PhDs are like becoming the world expert in a very, 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 very narrow area, and that speaks to like having this focusing down.
yeah. When
Yeah.
Joshua and I caught up at SuperCon, and it was Joshua. It was so wonderful to see you after all these years and the pandemic and all of
Oh
the
my
rest. You
gosh,
know, it
same.
was just like, but
Yeah.
I hadn't even thought about the fact that like SuperCon was the first place I picked up a soldering iron since I left grad school in December. Like
Yeah.
it had
Yeah.
been
Wow.
11 months since I
And
had
that
picked up a
and that's
soldering
really
iron.
that's really saying something because Zach used to not do anything except that at SuperCon. It would be like Zach's just sitting at the table
Yeah.
soldering the
Well,
whole
and that's what
time.
it
And
became that again, and it was like, oh my, it all came back. It was wonderful, but yeah, it was just like a total hiatus. Just like I can't, and I tried a couple times. Like I tried to get a little workshop set up in my apartment, and like no, it all stayed in boxes, and it just was painful to take out for a while.
huh,
Like it was weird.
Yeah. I think that checks out.
huh. That's terrible. I mean, I'm sorry that happened. That sucks. I mean, like, go back to the weaponized piece real quick. So like,
Oh yeah.
how do you see it as being weaponized? Like
Oh yeah.
because that's
Yeah.
a really powerful description of it. I think.
I think I think for me, projecting was something that was very near and dear to who I was. And then to see it go off and do something for other people that was beyond what I had originally imagined it being, which was like for me, like this is kind of projects for me. I've said this before to like friends. It's like a manifestation of the self. Like, this is
Mm,
me in this
yeah.
project. Like, this is me in this little remote control GameCube that drives around.
Yeah.
Or this is me in this like little animatronic tentacle that I made.
Yeah.
And but I realized that like I was doing this, I was kind of inextricably going to be tied to to something else. And I realized I had this question of like, do I want to be? Because a lot of these came from my head. Do I want that to be tied to other things, to another idea, or
Mm,
do I want them just to be mine? Yeah. So I think that's kind of where the weaponized comes from, where it's
yeah.
seeing my joy poured into building things, being kind of used for other reasons.
Does this? So I mean, so you're both in industry now. You decided to move out of grad school, and that's totally understandable. And then you're both in industry, and I'd love to hear about that because you're both doing really cool work. But does it feel the same when you're at the job now? Like, because that's kind of the difference I'm curious about. Like,
That's a great question. I think so. There's like a before and after here that I can actually reflect on, which is before grad school, I worked for a company where a lot of stuff was trade secret, and I
uh,
wanted to go to these meetups and talk to people what I did and this cool project problem I solved, but I couldn't. So what I did is there was work stuff that happened at work, and then there were projects that were kind of a different field, kind of different subdomain of engineering, and that was like the fun stuff. And so that was
Mm.
where like I was doing mostly software at work, and then at home I'd go to this like garage machine shop that I had made with a bunch of tiny machine tools, and that's where I was building my laser cutter. So that was my back and forth. Now I'm in this like very privileged spot where the things that we're doing at work are by and large open source. Like the intention is I work for a nonprofit, and the intention is that most of our stuff is going to get pushed out into the world. And part of that is because it's a science organization. We want to prove that the reproducibility of our stuff comes from like a very good kind of food chain. Like the food chain of getting this data
Mm.
is all sound and reasonable. And part of that is sharing kind of the core work that we do, including things like drivers, other pieces of software, and even hardware designs, which is kind of mind blowing. So I think I get a lot of fuel from that too now. And it ends up being a really special sweet spot.
But is it? Are you? So you said you're not still projecting at home, and is it because you're? I mean, let's be honest. Some of this is burnout, right? You guys sounded like you were very, very burnt out. But is it because you're no longer burnt out and you just are getting kind of the design jollies at work? That's what I call them, design jollies.
It's a good one. I
That's
like that. I'm
great,
taking
Chris.
that.
Yeah. Go for it. Or you still, is it the residual of like you still can't pick up stuff at home because of the kind of the scars?
I think what I found now is it's a little bit more fleeting. Where
Okay.
I do get those design jollies at work. That's true,
Yeah. That's
and I
great.
was not
Yeah.
expecting that either. I was very
So you
lucky.
were expecting kind of just a job versus like fulfilling.
That's kind of what I was expecting, is that this would be a
Yeah.
job, a good like recovery mark to move on to being able
Yep.
to take on like harder projects again. But it ended up getting really deep really fast, and
That's great.
I'm grateful for that.
And we should
Um,
say what it is, as you said at the beginning, but it's the Allen Institute, which is Paul Allen of Microsoft fame, who passed away, I believe.
yep.
Yeah. And you guys do like brain research and stuff like that, right?
Yeah, so the Allen Institute is a neuroscience organization. There's multiple subdivisions inside of the Allen Institute, and I joined the newest one, which is called the Institute for Neural Dynamics. And what they're interested in doing is, at least one of the projects that we're working on right now is like a high resolution, high fidelity images of the brain. Like, and we're talking the whole brain,
Mm.
and the whole brain, and in this case, the brain is a mouse brain. And so
Still pretty big though.
Mhm.
still
Still a
big.
lot of neurons.
Yeah, a lot of things to look at. Yep. Yeah.
Yeah, and so prior research, people had, and I mean, I am not a. This is like kind of what Zach said. I'm just a fabricator.
Yeah.
It's exactly
Yeah.
that. Like I'm just the
Yeah.
engineer here, where so my crude. Oh man, this is gonna sound. People are gonna squirm when they hear me talk about neuroscience. Sorry, I apologize in advance.
Well, I have no knowledge, so don't worry about me.
Okay,
my
so
my science knowledge in this area comes from Zach being on the show however many years ago talking about Neuralink,
hey,
or not Neuralink, the whatever it's called. Sorry.
That's great.
yeah, so I think basically a previous project had kind of mapped all of the genes in the neurons in the brain. And so the idea here is we want to know what are the ingredients of the neurons that are inside of a brain. And so the new project currently is kind of this question of like, okay, we know we have all the ingredients. It's like you took a machine, you melted it down, you were able to find like the constituent ores of what the machine was made out of. But what we don't know is like where are these genes expressed spatially in what neurons? And so this question of like, let's say you like move the camera over to any neuron, the question is now like, okay, what genes are expressed in this neuron? And so in order to do that, what we have to do is first take a really good picture of the brain, take a picture of the brain that's tagged with so that certain genes that are attached to certain neurons light up, and you do that with a few different genes. And once you have about four or so, you can use it as a barcode and say, okay, this neuron has these four genes. We think it has the rest of these genes too. And suddenly you have this mapping where you can apply, what genes are on what neurons from a particular subset of neurons that you can tag with, and basically you make them glow according to a certain laser channel. And so the part that I work on is basically like a reverse 3D printer. It's a microscope. It's called a light sheet microscope. No, it really is.
Yeah.
where you have a camera and
You
then
got to keep the
orthogonal.
thread going throughout the life. I mean, that's great, man. It's like, very precise, like you mentioned.
I just imagine like a 3D printer with a tiny vacuum on the end of it. I know that's not what you're talking about. Sorry, continue,
Yeah.
Joshua.
No. I think the way I would describe it is kind of like a reverse SLA 3D printer
Mm.
in a way.
Oh, okay.
So
Yeah, so instead of like taking or like having a screen that like shoots light into goo, now you take a slice of goo and you extract light from it.
kind of actually. That's actually
Yeah. All
really
right.
close. Okay.
All right. Great.
So you got a camera. You have a brain which has been cleared, and what that means is that it's mostly translucent, and there's been a chemical process, which is basically magic as far as I'm concerned. There's a chemical process that will remove most of the cellular material except for the neurons and their links to other neurons,
Yeah, that is magic.
Whoa.
which is
Yeah.
like magic, right?
Wow.
And so
And
now
it
you
stays
have a
structurally relevant too, right? I mean, like it stays in
yes,
place.
it's
That's
it's
crazy.
That's
embedded inside of a gel. And
yeah,
so it's
that's
retained
nuts.
its shape, it's
Yeah.
retained the pathways of the neurons, and it's retained the neurons, but everything else is gone.
Unfortunately, the mouse does not survive the process.
It does not retain the mouse.
in case that was unclear to people.
Yeah, so we're taking pictures of brains of dead mice. So just to,
Oh,
that's a very
sorry,
important part,
mice. Yeah.
at least in this machine.
Yeah.
And so yeah, so you have a brain that's submerged in goo essentially. You have that goo inside of a chamber which can move around in X, Y, and Z. And then what you
Mhm.
do is you have a camera looking in one direction and a sheet of light that is orthogonal to the
Hmm.
camera that is in the focused field of view of that camera. And what you do is you move the sample and you time the laser such that you turn on the laser, you image a very small like tile of the brain, and then you move the sample in X and then in Z and then Y and then X. You move it a little bit and then you shoot the laser again, you take another picture, and you do that a few million times and you have a volumetric data set of your brain.
That's awesome.
And what's really interesting about this is the way that actually that camera takes the picture. It's using a rolling shutter camera. So the first thing to keep in mind is that the sample's not moving; it's stationary. And what they do is, it turns out, so if you were to take a light and take a picture of a really small, tiny thing, and you just flood the image with light, you get a bunch of unwanted reflections.
Hmm.
And the reflections are coming from the light bouncing off of different features inside the field of view. So you're taking a picture of a tiny thing, you flood it with light, and all these reflections bounce around, and you get a picture with lower contrast. What some very smart person realized is, what if I used a rolling shutter camera and a scanning laser, and I move the laser such that when I turned on the rolling shutter, the pixels that were being turned on were exactly where the laser was at that point in time. Then I scan the pixels and I scan the laser, and what I do is I create an image from that. And the result is that you get way fewer reflections
Hmm.
because the light's only where it's supposed to be. And you get a way higher contrast image, which is way higher quality. And that's how we take the
Hmm.
picture.
But you have to like be set up to synchronize your like
Yep.
CCD
Yeah.
shutter scanning
Yep.
with like your laser scanning, which is
That's exactly
wow.
right. So you have to drive,
That's
all
nuts.
of those have to be driven in concert, where the shutter gets turned on, it starts rolling, the laser starts moving in the field of view of the camera. And so I think one of the things that I haven't mentioned yet is, like, this is a lot of engineers, and then there's a lot of scientists upstream and downstream who are processing the
It's a lot of
samples.
data.
And
That's
then
so much data.
Yeah,
yeah, oh
that's
My
yeah,
God.
yeah.
oh
Well, this
yeah,
is this is what I remember from Joshua telling us this at SuperCon. What were the numbers? It was like 100 gig per like picosecond or something. It was like some crazy amount of data that I was blown away by.
the data set for a mouse brain is about 100
Oh my
terabytes uncompressed.
God.
Yeah,
Boy.
Yeah.
that's not a small amount.
So what we have to do is we have to compress them online. While you're taking the picture, you want to squeeze it. If possible, you want to see if there's a way to squeeze it before you upload it to where it's supposed to go. And the thing is, like, the data set is so big that you can't even hold it on the computer that's taking the pictures. So you have to plug it into a bigger ecosystem. In this case, you have a bigger network, and you compress it as the picture is being taken, and then you send it up to the network, and that's how it ends up working. And so, like, there was a person who sat down and said, okay, like, generally this scheme of like this network and these components and this data rate, all these numbers should check out. And then there's folks who are really good at aligning the optics. There's optical engineers who do that. And then I've been working with a group of, I guess it's like 3 of us total, who are basically, we do like the drivers, we do the kind of the acquisition and the online compression. And then there's someone else on our team who's doing the GUI on top of all of that, so that a scientist can walk up, stick a sample in, define some coordinate XYZ limits, and then say go. And then a couple days later, you come back and you have a bunch of data in another
A
drive
couple
that
days.
allegedly
Wow.
has some beautiful
That seems
pictures.
fast for that. That's wild.
Yeah.
Wow, that's incredible.
Yeah, there's some secret sauce that I can't talk about yet. But the project is going to be released online. There's going to be a preprint with the code.
You can start downloading it now. It'll you can finish your download at the heat death
Yeah,
of the
aren't
universe.
those like
my
the? I mean, at some point you get to data like just total file or database sizes where like the fastest way to get data is like put hard drives in a suitcase
Put
and
on
put
a-
someone on a
yeah.
plane.
That's
Like,
right. Yeah.
that's still our like that's still the best we can do as humanity, right?
I mean, you could send a DHL.
Oh, right. Yeah, that's true.
yeah. But then, free flight.
I've heard of that. I can't say that we've done that here, but I've heard of
I
this.
think I heard about
because-
when they were doing the black hole picture reconstruction. I think they had to do it then. They had
Oh, yeah.
because they had all of these giant interferometers that they had to coordinate like globally. I think I don't know. I just remember it in the context of that project. Is someone got on a plane with like a suitcase full of hard drives.
Wow. Okay, so I'm going to be honest here, guys. I was so enthralled hearing Joshua talk about that. I have no idea where we were in the conversation other than cool things that you've been doing post grad school. So that's awesome. Zach, I also know that your thing is awesome. Maybe you could tell us about that so I can I'm going to try not to marvel at yours. I mean, I'm still marvel at yours, but I'm going to try and remember where I was in the conversation prior to that. But what are you doing now that we can hear about? What are you doing now?
Yeah, sure. So I work for a fusion startup called Commonwealth Fusion Systems. They're a spinoff.
Fusion startup, as one does, right?
There's kind of a lot of them now. It's like Fusion is having its.
I've heard that. Well, I've heard it from you.
Yeah, but there's Fusion has been around. I mean, people have been studying Fusion for 70 years. I think it was when they started building fusers, and like it's kind of this generational thing where like once in a generation there's like this big push to do fusion, and like this time it's in the private sector. So there's like
this time we're running out of time.
well, so but what's interesting is like fusion is really complicated. I mean, it's like it's hard to get it to work in a way that's useful and that actually gets useful energy out. I mean, we don't. You're basically you're trying to overcome electrostatic repulsion. Like you're trying to get nuclei of deuterium and tritium to get close enough to fuse, and like you need to overcome the fact that in a plasma you've stripped electrons off and they're all positively charged, and like you got to get them really close together. And like stars do that with gravity, and we can't make gravity, so we have to do it with really strong magnets, and that's kind of the crux of the problem. So back in the 80s, Gorbachev and Reagan like shook hands and created this project called ITER, the International Thermonuclear Experimental Reactor, which they designed to build in the south of France, and like they're building it right now. So it's been a generational global project that has that they realize that basically like they learn more about fusion plasmas and like confinement, and they realize like to get this to work you have to make the vacuum vessel and the plasma itself this size. They did the scaling calculation based on what they knew and based on what magnets they had. Like, okay, our vacuum vessel that needs to be at like 10 to the negative a lot needs to be the size of a 5-story building. So they're building a cryostat that is 100 feet tall and 100 feet in diameter, and like the whole machine weighs 22,000 tons, I think. I mean, it's a huge machine. So that kind of like shut down a lot of, I mean, there's still like a ton of plasma physics research and so forth, but like the idea of getting more energy out of fusion than you put into it like was all on ITER. It was like, okay, this is what the math tells us we need to do, so we're going to build this enormous machine. So what our company does is we That was kind of built using the type of magnets that you could use at the time. So then they were using niobium tin and there's another alloy, but they're considered low temperature superconducting magnets. They're actually the same kind that they use in NMR magnets. So they cool them with liquid helium and they get them up to, X Tesla. But they're limited in how powerful the fields can be. So a thing I've learned about superconductors is that not only do you have to get them below a certain temperature, but you also have to keep them below a certain critical current, and you have to keep them below, under a certain magnetic field density. So there's several parameters that make superconductors, work at a given field strength. So what CFS is doing, and we're not the only ones. Other people are talking about using these types of materials too. Is we're using higher temperature superconductors, which you can run at liquid nitrogen temperatures, but more importantly, you can run them to higher fields in like higher ambient fields at higher current densities. And it happens like the scaling law with fusion gain scales as the fourth power of the field strength. Yeah, right. So like if you're doing engineering, you're like, oh, a fourth power. I should look at that.
Right? I should run away.
Right. Yeah. But like the challenge is that like niobium tin is like a wire, and Rebco, rare earth barium copper oxide high temperature superconductor is like a micron thick ceramic coating on like a metal tape, So dealing with high temperature superconducting tape and using it to actually make a useful high field giant magnet is really difficult. So I joined.
And
go ahead.
So sorry, most of my fusion knowledge comes from the terrible movie with Val Kilmer and Elizabeth Shue called The Saint, which is completely wrong. So take that as a reference point here. The more energy that you have to put in than comes out, right? Two questions about that. One, is the energy mostly going to the magnet? Or is it going to like cooling systems, or where's the energy going?
So you put energy into the reaction to get things hot, to get them to move more, to get them to encourage them to be closer together, and you get energy out by combining. When you can combine a deuterium and a tritium, you spit out neutrons, and like the neutrons are what carry the energy out.
Okay.
And then you absorb these neutrons, you moderate them, so you slow them down, thermalize them, and you extract that energy as heat. Yeah, there's kind of a lot to
it. Okay. So the in. So you already answered the second question I had, which was the out.
Right.
The in. Where is the energy that you're putting in? Is it electricity that's basically going to the magnetics?
So there's a lot of ways you can do it, but to start with, you form a plasma in your reactor, and then the plasma basically becomes the secondary of a transformer. So you can inductively drive current in the plasma up to like the mega amp range, substantial currents in the plasma, and you just get resistive heating in the plasma. But at some point you reach the limit on that, and you have to inject energy other ways. So the way we do it is by injecting RF energy. So we have a 50 megawatt RF generator,
which is also how you make plasmas inside of etch chambers.
Right.
That's what I learned in my plasma days.
Oh, right. Yeah, because you were at Samsung, right?
That's right. Yep. In the dry etch group.
So we have like a central building where our tokamak is, and then one of the buildings next to it is where we have a 50 megawatt RF generator.
Whoa!
So then we couple RF energy into the plasma using antennas in the vacuum vessel.
That's crazy.
Yeah, just a casual 50 megawatt,
just hang out.
Yeah. So that's part of it, and then.
Fun fact: all the holiday lights, they light themselves in the facility, so they don't have to decorate.
Right, exactly. And then in an eventual power plant, you absorb the neutrons. There's different ways you can do it, but like the notional plan is to absorb them using a blanket of liquid salt. The liquid salt circulates around the reactor. It moderates the neutrons.
Yeah.
And you use a specific type of salt.
Yeah, that's like a heat exchanger.
Then you can run the molten salt through another heat exchanger and like use it to boil water and turn a turbine in the rest of it.
Boil water. Yep. The old standard.
All the quote unquote boring things. But the salt is also has beryllium in it and lithium, and you can use that. There's a neutronics reaction that produces tritium, so you can produce some of the fuel for the plant that way. Because deuterium is pretty easy to come by. It's just like hydrogen with an extra neutron, and it's part per million quantities in seawater, but tritium is a lot harder. You have to make
Seawater.
tritium.
It's always seawater.
It all comes back to seawater, man. Yeah, so I do instrumentation and controls for the machine. So there's a class of instruments called diagnostics that actually poke and prod at the plasma itself and like basically act as the inputs to all the control loops for plasma control and like tell us how many neutrons we're producing. So those are all like the interesting scientific instruments. I work on boring instruments, which are like, is this cool enough so that we don't quench our magnets and like we're not heating up too much from neutrons, and like how is the structure looking, and are we exceeding like our structural margins?
Has the building melted down yet.com.
Yeah, I mean, so a cool thing about fusion is that like it's so hard that the second you make like the slightest mistake in your control, the plasma just like disappears. And like there are things like disruptions, and you know, there are minor hazards that can be associated with that, but it can't run away from you. Like it's not it's not going to self-sustain without very
Doc Ock
yeah,
was
like
not correct.
it's not like a
in,
fission
Spider-Man
plant.
2.
Yeah,
I just remembered all of the other references I have to Fusion, which is
Fusion
bad
360
superhero movies. Yeah.
Totally. It's a CAD program. You know, it's everything.
Yeah, totally. Yep.
Yeah, so it's interesting. I'm learning a lot about neutron radiation and cryogenics and vacuum systems, and also it's a big project. Like, you know, I think we're well over 400 people now, which is a lot for like a 4-year-old company. And we're just about to move into our new headquarters. So we like are, you know, building a campus, and like it's a very fast growing operation. It's really interesting.
404 years is super fast.
Yeah, it's more than doubled since I started, which was less than a year ago. So yeah.
Wow. Yeah, that's
going,
startup life on the
well,
we
want to
sure.
that's great. We want to turn it on and like demonstrate net energy by the end of 2025. So it's an ambitious target.
Right, because you also need to raise more money.
That's the other part of that too. It's a private company.
We like that sort of thing.
You know, we raised what we could for Spark, which is the machine we're building now. But Arc, which is the machine after that, is, you know, we got to build that afterwards.
So you guys are making an Arc reactor.
Yeah, it's kind of this.
Is that correct?
Kind of a backronym from that whole world, right? From etc. Marvel person, Iron Man. That's the one. But it stands.
Got it.
Yeah.
I mean, when you get that many nerds in a room,
but it stands for affordable, robust, compact, because it's smaller than here, because it's not the size of a 5-story building. Yeah,
cool. It sounds like both of you have found very interesting and rewarding roles. Do you think it would have been possible without grad school? Did grad school open the door for these things, or, you know, network sort of thing? Like
for me, without question, like going to MIT, and like the Diamond Rotor project was like in the magnet lab, which was at the Plasma Science and Fusion Center. So it was like via that I kind of was adjacent to it.
You have similar coworkers now?
Yeah, it's all like this weird closed, like kind of tight ecosystem. Although I really like learned about the company when I was like reading a New Yorker article. So you could also just subscribe to the New Yorker, and you'll hear about interesting things.
Yeah, that's right.
I'd say as opposed to Joshua, we're really like doing design work and testing and like, you know, big project engineering. So I'm kind of going back to what he did before grad school, which is separating my like hacking and making and doing that separately. So I've joined a maker space that is just opening up, and I'm excited to like get back into that and start making things that are not related to work.
That's awesome. You get to be part of the culture. I think it's always a really great part of it.
Yeah, it's a group called Artisans Asylum. They had like a big space before the pandemic, and then they had to move out of that space, and then the pandemic happened. So they were kind of shut down for like 3 years, and they had their grand opening tomorrow. Like, and I moved into my studio like last weekend, and they just got their certificate of occupancy and are like just plugged in their laser cutters. That's and great. Like have a few hundred members. So like we're gonna like be able to create the culture we want to, which I'm really excited to be a part of. I've never been a part of an organization like this. Like I've always done my making and hacking like either in grad school or like in my basement, you know. So it'll be great.
Oh yeah, that'll be a blast.
Yeah, Artisans has been awesome space. I mean, I did a couple events there.
Yeah, the irony is awesome. That like the landlord decided they wanted to like go from supporting artisans to like attracting tech startups, so they like jacked the rent way up, and like now that is one of our offices for CFS. So it's there's a weird like small world thing going on, but
yeah,
it's very strange.
Joshua, what about your role was tied to your work as well, or no?
Ooh, interesting. Let me think. I think when I think about like, what are the skills I'm using at work on the day to day, I think it would have been pretty straightforward to go from the job, skip grad school to the next job. But whether or not I had the right qualifications to get through the door in the first place, that I think is really tricky to answer.
Right.
Because I think different places weigh degrees in different ways. I think I could do the work without the degree completely. But whether or not I would be considered in this pool of applicants with other people, I have no idea. Which is actually a really good thing to bring up, which is kind of this sobering idea that, like, as an engineer, I have a tremendous amount of flexibility in that really I can get away with a bachelor's for
Yes.
for pretty much for pretty much it. But if I wanted to go into, let's say, a neuroscience, if I wanted to go into neuroscience for science, or if I wanted to go into biology, or if I wanted to go into some of the other sciences, like, you need a PhD to get into the door to
Table
even be
stakes.
considered. And that's
Yep.
something that, like, yeah, I have like, being an engineer and being able to make these comments about grad school and being able to weigh it as like, oh, is it worth it? Is it not? That's this is all coming from an
Right.
engineering point of view. So it's
Totally. Yeah, my wife reminds me of that as well, as she has an advanced degree, and she's like, you could do it. You could get a job. I couldn't have gotten a job. I was like, oh yeah. Okay.
yeah, and that's totally a big part of it. Yeah, so I think I could do the work from the first job to the next job, skipping grad school, but I may not have been considered. And I think the other thing too is that, like, I think it was the right place, right time, where I was
Sure.
ready to leave right when they were ready to create this, like, new wing.
Yeah. Was there any networking involved? I mean, how did you find out about it? That's another thing I always think about is, like, grad schools. I always think about this for like MBA programs. Like the primary thing for an MBA program is the network. Like if you're going for other stuff, you're going to get other benefits, of course, but like the network is the number one thing. Grad school for engineering, I feel like there is network, of course, like Zach mentioned, but there's skills and just publications and all the other stuff. So
Yeah, I think it was the right place, right time. I was doom scrolling Twitter, and it turns out that the person behind the interview I had met at a hardware happy hour meetup in Seattle.
nice.
So that's how we had known. That's how we knew each other before we did the interview together to join the team.
Wow.
So I think it was serendipitous in that way. Yeah. So I'm not sure if that answers your questions. Yeah, there was certainly, I would say, a
Well,
little bit
would
of
you have been
networking
doom
involved.
scrolling Twitter quite as much if you hadn't have had the stress of grad school?
There we go. No,
Ooh,
no.
interesting.
Something like that. No, I have always been a sucker for, I want to go meet people who do projects because I
Yep.
want to hear other people share their joy and what have they been working on and learn from them, and also kind of share that feeling, because it's very, like, I don't know, it's like a very low level thing in my brain where I'm like, oh yes, I made a Blinky thing and it makes me feel so happy, and
Yeah.
let's go find other people who do the same thing. But I think as a consequence, like, if you I think there is some element of, there's a networking part of going to these meetups that I don't necessarily go for them for that reason. I came to bring the project and listen to other people talk about their projects, but I think there's definitely a benefit to going to them, which is
Yeah.
networking based.
Well, I hate to break it to you, but the things that you described before, you said I go to these things for the non-networking benefit. That's actually networking in our
I
space.
feel like
Oh, really?
Talking about
I
your
feel like
project.
the best
Sorry
networking
to break
comes
it to you.
from like not going into networking though. Like you don't walk into it
Yeah.
because you want to go
Yeah,
networking. You
totally.
go into it because you are excited to see what
Yeah,
people are doing. And
cool stuff.
I will say that, like,
Yep.
even engineering school though, you can do networking. Like I had a friend I met in undergrad, and he ended up starting this podcast. And yeah, anyways,
Yeah.
his name is Chris Gamble.
It's true. It's true. That's right. Thanks for closing that loop there, Zach. Yeah.
Yeah.
Oh, you made a circle.
Speaking of closing the loop, so we are about to kick into the before recording, which I have no idea if it's any good audio wise or what these two guys said. I don't know, but what's the coupling style you guys
Kinematic.
talked about?
Or
Like
Kelvin
kinematic
coupling.
Is that what it's called?
Right.
Is
Yeah,
that
the one I made was
nice.
the Maxwell
Okay.
coupling.
Maxwell? Okay. So, anyways, here's my proposal. Because I am a tire together of people, I suggest that you two start a podcast. Usually, I do this for people after the show, but I'm going to do this on the show for extra added pressure because you both are working in similar spaces, you have similar backgrounds, and you're very amiable to talk to and with one another. You guys could talk to one another all day, I'm sure too. I think you should start a podcast. And here are my two suggestions. One would be kinematic coupling would be one, but maybe that would be kind of weird. But the real one, I think, would be here's the title: Post Doc, right? And then you guys could just call it postdoc, and it also acts like a postdoc. And you could talk to people like it's, if they've also jettisoned a PhD program, and then you could talk about interesting people that are in industry. Of course, you would not step on my toes because you would clear every guest with me. You'd also feed me guests. This is also why I got distracted when Joshua was explaining his project. So
postdoc, it would make so many postdocs angry too, because they'd be like, "You didn't even get a doctorate. Like you're not a post. Like no,
yeah, exactly.
They would like rage listen to us, and we'd get more listeners. That's great.
I know. But think about how good it would be. Yeah. Anyways, think about it. So, because we're in the present, I will say thank you both for being here. Thank you for sharing your stories. Thank for sharing the the ups and the downs. It sounds like it was a tough time, but ultimately, you guys survived it, and I'm glad for that. And seeing what you're doing with all this work, it's been really great.
Yeah, well, thanks for chatting with us. I mean, I think the other thing too is that like we just went through a pandemic, and that's absolutely
Oh yeah, we forgot that. Yeah.
In like some ways, like doing the work on Jubilee was like that was very healing in a way during the pandemic when I had nothing else to do. I was like, well, might as well make some instructions.
Yep.
And so like I can't untie these two things from each other. They all happened together.
Pandemic grad school was I was there for 5 months, and then it like I remember there was a weekend and we got a note from MIT, and they were like, all the undergrads are leaving like in 3 days, and we don't know when you're coming back. So like seniors, like say your goodbyes and like go back to your parents' house. And then I spent the next like 2 months trying to figure out how I could do like pandemic relevant maker projects just so I could get back into like fabricate things. And then we like made face shields and all the other bullshit that people did. But it was purely because we just like needed to keep making stuff.
You need an outlet. Yeah.
But you can't untie grad school from the pandemic for either of us, I think.
Yeah. Well, like I said, I'm glad you both survived, and thanks for being here. Let's roll the tape on 3 years ago. Here we go.
Let's do it.
Hi, this is Chris, and I'm with who am I with?
Zach Ferdine.
Joshua Vasquez.
And Josh and Zach are both people that I know from industry, and you're both going back or have gone back to academia. And I want to get your opinion on this. We're at Teardown as well, so we should mention that. So what was your motivation for going back to academia?
Ooh, it's a long story or the short story? Let's see if I can
short-ish story.
Yeah, let's condense it. When I was leaving undergrad, I thought I was kind of 50-50 going deeper into academia or going into industry. And for me, I wanted to teach one day, go back and teach. But industry opened the door first, so I said, okay, let's go here. And I did apply to places. I didn't get in anywhere. So I thought, no problem. I will make my own adventure in my garage. And so I started building machines in my garage, and then met Prof. Nadia at a SuperCon a couple years later.
Oh, and we've had Nadia on the show as well, Dr. Nadia Peak. Yep.
So I call her Prof. Nadia now.
Oh, really?
Yeah.
Does she like that or no?
I think she's okay with it.
Okay, good.
For me, it's very endearing, but plus with a little bit of respect.
Yeah, right. It doesn't sound weird to the other students as well, but it's still like casual enough that you're not like
exactly.
Oh, great sage.
Right. Yeah. So she said, hey, I'm starting a lab at UW. And I said, wait a minute, like, you're starting a lab at UW, like, do you need some students? Like, maybe me. And she was doing machine building, and I thought to myself, wait, I'm doing this in my garage. Let's do it full time.
Let's do it for reals.
For funsies, and see if other people can reap the benefits of what we do too.
Yeah.
And that I think was really cool.
Cool.
So I'd say being able to go back, work on something that I was really interested in, that I was doing in my garage for fun, and be able to add being able to contextualize it, add meaning to like why are we doing this? What are the patterns that other people that I'm doing, that other people are doing, that we can tease out and make explicit, and teach people about.
Cool. Zach, what about you? So you are going back?
Yeah, I'm
process.
gonna start this coming fall after being out in industry for 12 years, and I initially, similar to Joshua, was torn when I graduated between staying in academia and going out into industry, and I ended up at some point getting into my head I wanted to be a manager. I wanted to be like a factory manager. I wanted to be in operations.
You were in sales for a while too, weren't you?
Yeah, so I was in a rotational management development program, and I was doing factory floor management as a production supervisor at a forge. And then for a while I was in sales, selling industrial instrumentation and control valves and such. So I had a territory in a car, and I drove around rural Minnesota, and I went to sugar beet plants, and I sold them radar level sensors for their bins, and then I started a company. We've talked about that before.
That's right. Jack's been on the show before. We'll link that.
And at some point during the course of my work at NeuroTinker, I realized taking deep dives into very specific, interesting subjects was the part about it I liked the most. And commercializing and selling the product and optimizing the cost of a BOM and running a business turned out to be the parts that interested me the least. So when we had technical problems and I needed to test hypotheses and do interesting, novel, deep research, that was when I was happiest. And then like Joshua, I was at the Open Hardware Summit last year, and thanks to Noah Feehan and Clarissa from Kickstarter, they grabbed me at the last moment when they were taking a last-minute lab tour and dragged me along, and I met my advisor, and he showed me around the lab, and we had dinner, and then I found myself applying and got in.
Right, which is interesting, too, because Nadia also used to work in the lab that you will be going to, and so it's like you guys are connected in that way as well. It's like a lot of machine building and machines that build machines. Yeah, so everybody's doing it these days, really. But yeah, no, it's really cool, and I really like that idea. I mean, it sounds like the deep research piece. I consider it myself, but I think some of it's interesting too because of the lifestyle piece. And you've both been it's like a conscious decision of no. Well, this is a thing we're going to do. It's going to be a chunk of time that I'm willing to donate or to dedicate to this thing. And
did you say donate?
Well, it's effectively donate.
I call it the 5-year mission.
Okay, yeah, I mean like that, right? And you got a head start on Zach, so that helps.
Yeah. Okay, 4 years.
Yeah. So what was that mindset change though? I mean I guess maybe Josh, you're a little closer. Would you still recommend it after being in it? Or should Zach run away screaming right now?
Joshua, if I could jump in and quote you from our discussion yesterday. Right. And you said, well, the first year is the hardest, and it gets easier after that. To which I replied, well, you've only been in it for 1 year.
But to be fair, I was quoting someone else.
Okay, yeah, fair enough.
So a lot of hearsay at this point, huh? At some point, someone's going to be like, oh, no, I was totally wrong about that. That last year's the hardest.
Last year, yeah. Oh, no. Just got to get that thesis out.
Right.
Okay, so I think our lab is starting. We're in our first-ish year, and what was interesting for me was there was such a huge overlap with things I did for fun and with the things that I was going to be doing for research. I was thinking to myself, okay, am I going to build a lab at home and then have a lab at school? Where are the tools going to go? And eventually, for a long time, I was splitting my time at home with some tools, and then going to school for other tools to get certain things made. And then I realized this is not going to work. Everything's going into school, and I'll just put my name on tools, and people have been pretty respectful about using them in a reasonable way, and that's been so going all in the beginning. As far as the physical things I can bring into lab was a little bit weird for me, but I think it's made it's been awesome for our lab because in one sense, by setting the tools, we're also establishing certain types of practices, and in my mind, I'm hopefully bringing in what I think are the best things I can bring forward from the get-go. Of course, I'm sure I'm bringing in bad practices too, but in the form of I brought in my McMaster catalog. So going all in and realizing that hey, I'm not going to have the garage fab lab that I had back in my last place when I was working. It's all going to be in this lab. That was different. But I think it's it's like going all in has definitely been a great decision. So all my machines live in the same makerspace with other people. We've got a corner in our lab, and yeah.
That's good. That's good. Okay. What about the actual research aspect? I mean, I guess it's more of a I don't know if you're publishing yet, or Zach, you're going to be publishing, but like, what is the actual requirement around that too? Because that's another thing I always think about is like, it seems like that's a very tough aspect of academia. What is it you think about when you think about having to like push your work out like that?
Well, so the lab I'm joining has a 20-year history and a research arc. So what I've learned about publishing has been from reading a lot of the theses and a lot of the papers that have come out of the lab that relate to the work I'll be doing there. So my main understanding is, seeing the rate at which papers have been produced and who's been publishing them, and seeing how much work goes into a thesis, and then thinking about my own abilities to produce that kind of work.
Yeah, publishing is one of the main mechanisms in academia where by which you are known. It is the means by which you establish the credibility to your name, the things that you do, and it is literally your contribution in many cases. And that's different and interesting for me because in the past, for me, my form of contribution has been maybe writing a piece for Hackaday, or maybe an open source project that I make some pushes into. Or just publishing my CAD files of something that I built.
Yeah, right. Like GitHub type, like open sourcing type of things versus a more formal method.
Right. And so in academia, the publication being the primary mechanism is kind of weird for me, where the CAD files and code are all I would say slightly secondary to the content that goes into the paper. So that's been interesting. There's... So publishing is going to be new for me, and it's going to be one of the main mechanisms by which we drive. It's how we're rated as where we are in the program. So you've done a certain number of papers by this certain amount of time. I think what's been strange and different is as we read more papers. We started a reading group earlier, and back when we started reading one paper a week at least. And what I've been noticing is that I'll see repeated patterns of people doing things in HCI. HCI is human-computer interaction. So there's a whole group of academia that does things with usually involving humans interacting with some form of technology. But what I've noticed is there's a lot of work that's going into HCI in the academic community that is almost mirrored in the hacking after-hours engineering community. And it's been very interesting that they actually don't cite each other. It's almost like they don't know. And for me, when I first realized this, I thought, this is so disappointing. I've seen so-and-so do this in their garage already, and they didn't credit them. But I realized at the same time that I might be the only one who has that perspective.
Yeah.
So
that's wild.
Maybe I'm supposed to go in and build a bridge.
Or steal some great work, one of the two.
yeah. Now that I know how it works.
One thing that Joshua said earlier about going all in on something like this just kind of stuck with me. Also, when I accepted my my offer, in order to accept it, I had to click a little button that said, okay, now everything that you produce, anything that you produce intellectually and design is jointly owned by your lab. You have a non-exclusive right to it, but so do they. And that was just a really interesting thing because I've always been able to separate my work when I was in industry or when I was running my own business.
So this is 24/7 no matter what, until you're gone.
That's certainly the impression that I got.
Yeah.
It's because most of the time you're going to be spending it in the lab anyways. My wife Donica and I are right now in the process of selling our house, and we're going to move into the graduate couples dorm that's a block from the lab. So we're not going to have our own equipment even if we wanted to use it anyways. So I'm only going to be using their resources, but getting into a place where everything I produce is not just owned by me is a real. It's like that was a real mind shift that I had to use, or that I experienced.
Yeah, that's a big shift for sure. I mean, does that? Oh, go ahead.
Oh, I was going to say that's really interesting that you mentioned that. actually one of the reasons I was going into academia, and again, this is a case-by-case basis, is because because UW actually doesn't yet have a policy on ownership of things. So I'm
skirting the system.
So yeah, I actually in industry, I remember building a lot of things and realizing, wow, this is so cool. But my hands are tied as far as discussing details of the design with people in the future. I can't give talks about it. I can't.
Right. Now it's like literally your job to give talks about it. Right?
Exactly. It's the complete opposite, where all of our work is going to be open source, or a lot of the things are already starting to distill out in the form of Thingiverse or things on GitHub. But I remember that being one of the reasons why I wanted to go back, is because I like talking about stuff that I've made, and that's something that's really fulfilling. Well, it's fulfilling for me, but I'll be able to do that within this lab.
Yeah, it's like I may have already said this. It's kind of like your job to do that now too. It's like if you don't do that, you're not doing.
Where are we gonna get the money from?
Right, exactly. Yeah. Well, I think about it like from I've been trying to build like a portfolio site. It's like, what can I even put on there? I don't know. Like client stuff? No, I don't get to.
Right, yeah.
Like, that's not a thing.
Well, that's I don't know. When I was in college, Chris and I went to college together, but we were 2 years ahead of me, so there was a group of engineers that were all in the same year as me, and we would sit around and just like talk about engineering stuff and interesting projects and interesting stuff. And like now, 10 years out of that, I'm still in touch with all of those engineers, and the most interesting things they're doing, they're not allowed to share with me. And it's just I got to a point where
think about when you work from GE is
yeah, or whatever other name your big name company that does really cool stuff that they're not allowed to talk about. I think. The lab I'm joining does have a much stricter policy, it sounds like, than Joshua, yours. I was reassured by the fact that I met my advisor when he was giving a talk at the Open Hardware Summit. So that ended up, that was a good sign, but I had a discussion with him at some point. It's like, well, some things get open source and some things don't. It's a case-by-case basis depending on the technology and what's being developed.
I think one of the things I've realized from industry, and I think Matt Berggren has actually mentioned this, is
Matt
that
Berggren, the Autodesk Eagle,
Yep, that
my
guy.
former coworker, supply frame. Yep.
Yeah.
Chris,
person.
cue in an eagle sound right now. Thank you.
That's actually a hawk.
I heard that.
The Colbert sound is always a hawk.
But that's the sound we want.
Okay, yeah. All right, hawk sound.
Thank you.
Here we go. But he mentioned something at a Hardware Developers Didactic Galactic talk maybe 3 or 4 years ago at this point about him noticing engineers solving the same problems in many different isolated environments and not being able to talk to each other about it, or not being able to share those.
Matt's really big on like design reuse, and he pulled that in. That's actually a feature of Eagle that I really like, is that design reuse kind of thing, the blocks.
Exactly, and I think he mentioned
he's very into that.
Something about IoT where I think he had a phrase where the world of electronics is not infinitely subdividable.
Oh yeah.
Something like that.
Yeah.
And that was a nice perspective shift for me, because I remember solving little small problems in industry at work on my desk and be like, hey, I got this working. And then realizing to myself that, oh, wait a minute, someone else has gotten this working too at some other company. And I would have been able, had we been able to share those designs, I would have been able to just download it and solve the next problem.
So yes, I agree with that. But some of it is also like, I got to do something at work, and I do find personal joy in some of those things. Like, sometimes when I'm stuck, and it's like, and honestly, when it's client money, here, what should I say? When it's like client money, I shouldn't be necessarily solving those things, but I have to say there is some personal joy in even discovering things other people have discovered before.
I completely agree. I got so much satisfaction
design jollies. Let's be honest.
Absolutely, that is absolutely true.
Yeah, and it does feel so good. But then I had to remember, like, okay, like if we want to do things farther down the line,
right.
What
Helping
are the next
humanity,
steps?
right. Yeah. If I, if we're in space and I'm laying out a DC to DC 5 volt to 3.3 volt switcher again, something's probably broken. And yeah.
For some reason, this reminds me of a really important point. Noah Feehan comes up again, that he said, try not to work too long between each endorphin rush.
Yeah.
So try to be able to split your project into little excitement chunks that keep you going towards the next step. And in some cases, those come from solving an existing problem in a slightly more elegant and probably far less cost-effective but very satisfying way.
Yeah.
And if it gets you to the next step in the project and the other option is putting it on the shelf, like, it's worth it.
Right.
Yeah.
Well, Noah's also done MIT, right?
Yeah, he was in the Media Lab.
Right. But I think that's another thing that I wonder about is like that. It sounds like from the people I know who've gone through it, it is kind of like open loop, like you're kind of on your own. And Zach, are the concerns about that, or Joshua, have you felt that of like how much there is like, well, just go find a new thing to do? Like, I would personally worry about that.
I actually, going in, that was one thing that I worried about, is that, okay, I remember thinking to myself, I'm going to be alone in lab solving a problem
that nobody else has solved, because by definition it has to be. Right?
Maybe, yeah. Odds are good. Or if someone has solved it, it has to be contextualized in a way that no one has contextualized yet.
Sure.
It has to be spun in some new flavor.
Right. That's stressful.
Yeah, a little bit.
Yeah.
But that said, I think this is definitely going to be the challenge of figuring out how. I think what do I really want to say? Figuring out the lay of the land, and then taking the next step forward, which is the step that is now on the shoulders of every grad student.
Sure.
I think figuring out the lay of the land, I have benefited from being in industry, getting a sense of the lay of the land a little bit.
Yeah. Yeah. You actually know what's really needed versus just what's the next research step too. So there's that.
Yeah, but I still do worry about best practices. I think I can easily hold myself up in a wall or in a corner and design things in one particular way for the rest of my time there, and realize that actually it's a bad practice. And while I'm doing that, someone else has a tool called SolidWorks Electrical, where the schematics are done automatically for them, or their wiring diagrams are automatically generated, and I'm
you're
doing it
drafting
manually.
on a
Yeah,
table, right?
I'm drawing. I'm scanning my pictures from my notebook.
Yeah. Zach, what about you? I know you're. I mean, that's the thing. Like, I asked you to do this talk, but it's like you're kind of coming into this. So
yeah, no, I guess I feel a little weird saying anything definitive about what academia will be like, being that I'm still a few months away from it. I know in speaking with other people that went through this lab and went through other graduate programs kind of in advance. I've been out of school for 12 years, so this is like it's a thing. I didn't know if it would be a good idea or not. The common feedback I got was that collaboration happens. In some projects, collaboration happens a lot, and sometimes it's in the lab, sometimes it's outside the lab, but like fundamentally it's your thesis, and you are doing all of the original work on your thesis. And like you may get some ideas from other people, but like it's really your thing. And
you got to put in the hard yards.
Yeah, and that's like an inherently isolating thing that you just have to learn to manage and pull in resources when you can, but it's still you. It's not the lab, it's you.
Yeah, so how do you go about finding something that's like never been done? I mean, like, is it just figuring out that next iteration, or I guess I don't know how iterative it is in academia too.
Yeah, I think the answer to this question actually really depends on who you ask and where, like what field they're working in.
How defined the field is, how formally defined it is, right?
Yeah, and is your contribution going to be an optimization of something that already exists, and you get a 10% improvement in speed or performance in some other way, or like resources that are used maybe, or is it something that no one's ever seen before? And that's I guess where I'm at right now, which is kind of in the HCI, human-computer interaction environment. That's a little bit more of an integration of many different existing technologies. So a lot of what I'll see is not someone pushing the technology forward, but the consequences of the technology forward by merging them together in new ways that people have never seen before. So that's actually what I'm telling people now, is that I'm not in grad school to push the science or technology forward. I'm here to push the consequences of them forward by changing them a little bit, and then having them engage with people in ways that they've not been able to do before.
I mean, it is amazing like how much stuff is. So like so I'm like a huge Ben Krasnow fan. So say we all.
Yeah. So say we all.
Oh yes.
But like every time he goes through like a research turn up here. Whenever someone's going through a research paper and like explaining the consequences or patents, like Ben does a lot too, it's like there's a lot of shit that's out there. Like, and I know some people are implementing it in, algorithms or pulling it in or licensing or whatever, but there's just so much out there that's just like, it's just sitting in a paper. And sometimes I kind of grumpily say like, oh, well, it's just academia, they don't do anything for the real world. But it's like, that's not really the job of academia. It is to do this new research thing, and then it should be applied somewhere. Like, so you look at like a Disney research paper, actually Noah, so he's also, right? Yeah, tagged. He's taking a Disney research thing and turning that into WEFT, right? That's what he wants to do is turn that into a thing. But there's nothing, Disney wasn't going to do that, not by a long shot, right? And so it is on the role of, some engineering corporation or or an engineering, bent PhD to make it more relatable and deployable in the real world.
Yeah, I think you'll see in the paper the kind of the related work and implications are those subsections of the paper are different sizes depending on what journal you're looking at.
Oh yeah.
And what discipline. And in some cases, maybe the implications don't matter so much. But in other cases, maybe that's the primary reason of doing the thing in the first place.
Yeah.
Well, and I think that's a big part of doing research is knowing the background for whatever you're studying. So it's reading papers and then telling sharing those papers with other people in your research group and them suggesting papers that you should read and trying to figure out how to pull all that together into a coherent arc that you can then extend. I think a great way that you can kind of hack that process is to read PhD theses. Because most theses include
Saturday night.
Yeah, no, exactly. I mean, there's a joke that like if you back when theses were like published in paper and stored at the university library, it's like put a $20 bill in your thesis, then come back 10 years later and grab your money. It's like you acts as a safe deposit box,
Right.
But like most compared to a lot of papers that are like 10 or 12 pages long and like really are designed to push. Have high density of information and like not a lot of background. Like a thesis might be 130 pages, and like 30 pages of that is a comprehensive literature review that talks about everything that they've studied. So you can take that.
It's like a genealogy.
Yeah, you can read that section, and then you can look at what they've cited, and you can read all those papers, and then you can go to the next thesis.
I believe it's called a rabbit hole.
Yeah, but it's like it's your job as a researcher to go down a rabbit hole. It's like. It's the biased random walk of like going down the right rabbit hole.
Yeah, and that's kind of awesome. Like that's partly why I want to be there. Someone's going to give me the time to actually go deeper in something that is very obtuse.
Super, super deep. I'll send you a link to this, Chris, but there's like a great webcomic that talks about like your progression through educational levels. So you have like your undergrad and you're like making a circle, and the circle is the boundary of your knowledge. And like you go to grad school to get a master's, and like that boundary expands, but it expands kind of in a biased manner towards one discipline.
Oh yeah.
And then you go and you get your PhD, and there's just like this tiny little thing that pokes out,
like
and that's the section that passes through the boundary of what we know as like humanity. So you have this tiny little contribution that is actually pushing like human collective knowledge forward somehow. And then the point of the comic was like, oh yeah, and don't forget to zoom out because it's a big circle. Like it looks like a line. You're so close to the edge of it. You have to zoom out and see that there's other areas of study. But I don't know. I thought that was.
I was
really
gonna say
compelling.
that doesn't sound like PhD comics, because then it would be like much more depressing, and it's like your
kind of
advisor stepping on you somehow.
There's a lot of
so warm.
cynicism in like internet grad school discussions that is worth avoiding if you're getting ready to go into grad
That's
school.
right. Yeah. You do that
Well-
about 2-3 years in, you're like, yeah, I want to bitch about this.
Yeah, I'll mention it's partly your responsibility to make sure that you're looking out after yourself. And I think if I were having a horrendous time, I probably would not stay there for a long time. Or also step one is figure out like what is the problem and figure out ways to help myself to make sure that I don't wake up every day feeling grumpy about what I'm about to do, because I feel like doing that for 5 years would be take a toll on me in some way where I'd come out jaded or like bitter about the world in general, and I don't want to be that person.
Yeah, you're very far from that person.
I agree with that.
Well, thank you.
Thank you for your
I've been in my
relentless
d-
positivity. It sheds off on all of us, and we appreciate
I've
it.
had my dark moments. The hair was in front of my face.
You don't know what I've seen. You do like Batman voice at that point.
Yeah, you don't.
I'm just imagining like stepper motors just flying all around your shop, and okay. Anyways,
Yeah.
It's more like chemicals, but yes.
Gotcha.
Okay. Yeah. Well, guys, thanks for telling me about this stuff. If people are interested in talking to you about your journeys back towards academia, because both of you are, you're definitely not as young. You're no spring chicken, Zach.
correct.
Yeah.
Correct.
Josh, you're younger, but not super young.
I can grow a beard now, almost.
Hey, you're getting there, man. I believe in you.
So, yeah, I'm working on it.
Yeah. Where can they find you online if they want to talk to you?
So email is joshua@doublejumpelectric.com. Or you can just reach out to me on Twitter. I'm there too.
Was it Joshua Vasquez?
I'm Poof Junior on Twitter.
Oh,
so
you see, you have to say that.
you
or
have to
else
say
we're
the
like,
whole thing.
what?
So it's POOFJUNIOR.
Okay, get the story on that next time.
That one's a little weird. Yeah. Yes. Yeah.
Yeah, and all my contact information is at zachfred.in. I grabbed a great domain, so I'm happy about that. Zachary.ferdine@gmail.com, or my Twitter handle, which is Zachwy, ZAKQWY,
Right.
which is a throwback to when I had a speech impediment growing up and couldn't say the letter, pronounce R. And unfortunately, the letter R is in Zachary, so I pronounced it Zachwy.
Super
And
adorable.
it stuck
Super
with me
cute.
forever.
All right, thanks, guys.
Thank you.
Thank you.